Welcome to my third lecture of electromagnetic waves. Okay. So, this is lecture 3. Let me start with a brief recap of last lecture. In last lecture, we basically studied, first we studied our Ampere's circuital law, okay, which is integration of cyclic integration of BdL equals to mu naught I. Okay, this is Ampere's circuital law. Next, we discuss this law in detail, totally how the line integral, what does it mean by path integral or line integral, and from there we just derive that not derive, we just stated that law because this is the law. Okay, this was not derived. So, integration of B dot dl equals to mu naught I, and then we discussed about Ampere Maxwell law. Ampere Maxwell law, which is more general form of the Ampere's law, mu naught I, this is correct, but we have to add another term mu naught epsilon naught and d phi e dt, where the phi, this is the phi, phi is the electric flux. So, it is the rate, flux rate per unit time. Okay. So, this is our Ampere's Maxwell law, and from here we studied then displacement current, which is ID displacement current. This is actually called the mu naught ID. So, ID is the displacement current is defined as mu naught d phi dt, and now the phi, definition of phi is integration E dot A. So, not E dot A, this is E dot dA. So, we can write it like after integration it will be EA. Okay. So, we can write that phi equals to, this is just q by, we have discussed in details these things, epsilon naught, q by epsilon naught, where q is the total charge. Okay. So, if we put it here, then we obtain that ID equals to dq dt. So, this is the displacement current as we discussed in last class, and after discussing the displacement current, we define our electromagnetic waves. What was the definition of electromagnetic waves? We stated that, okay, and at last we discussed the Maxwell equations for electromagnetic waves, but integral form. In first class we discussed Maxwell equation in its differential form, but in last class we just write down the integral form of the Maxwell equation. Let me again write it down because it is important, that Maxwell equations, okay, Maxwell equation integral form. Okay. What was the equation? The first equation was integration E dot dA, both are vector, cyclic integration, E dot dA is phi, and phi we have just derived that. Okay. This is just E A. Okay, if the area, okay, let me explain. This is not cyclic integration, but this is in general form. This is the general form. If we consider, as I discussed in last class, that this integration is actually the two types of integration are there. One is surface integration, one is line integration. This is the surface integration, because here this is the surface element. Like this, if we consider a surface, this is the dA. If this is the dA vector, area vector, and let us say here the magnetic electric field is working, this is theta, then from here in this area the phi the flux will be d phi, which will be E dot del A, right. Now, if we integrate over the surface, so we should use the surface integration, okay, the notation of surface integration, but here we can say it in terms of cyclic integration as well, but more general way we should write it as surface integration. So, then it will be that means the integration all over the surface. Okay, if we consider the line integration, then if we integrate all over the line, all over the path, then it means the cyclic integration, but as here it is the total surface, so it is better to write as the surface integration. So, E dot dA it equals to phi, phi means the flux, and we have defined in last class the phi is equals to q by epsilon naught if we consider in the vacuum. So, let us say in vacuum, then only it will be phi naught, sorry, epsilon naught. Epsilon naught is the permittivity in the free space vacuum. Okay. So, this is the first equation. What is the name of this equation? It is very important. This is the Gauss law for electric field or electricity. Okay. Now, the second one is again surface integration, but here it will be not E, it is B dot dA. It is always 0, which essentially signifies as there is no magnetic monopole. It is the Gauss law for magnetism. Okay. Next is, these are two surface integration, and now if we discuss the line integration of the same, then it will be dl, and as it is line integration we can use the cyclic integration form. So, E dot dl, this is the line integral of the electric field. So, it will be minus d phi b dt. This is the Faraday's law. This is the Faraday's law. Okay. And the last one is the fourth one, cyclic integration of B dot dl is equals to mu naught I plus mu naught epsilon naught d phi dt. Okay. So, this is the Ampere-Maxwell's law. So, these four are the Maxwell's equation in integral form we are considering in the vacuum. So, again we have discussed the physical meaning, physical interpretation of these four laws. Let me again state that. If we consider the first one, this means the there is a electric monopole, let us say, that means a point charge is there. Then the if there is a point charge, let me draw, let us say if there is a point charge, like here there is a point charge, if we consider there is a field around that point charge. So, if we consider the total flux around that point charge, that will be q by epsilon naught. So, this is just the divergence of that electric point charge, okay. Because E dot dA, this essentially signifies the divergence. Okay. Now, the second law means that there is no magnetic monopole. because if there is magnetic monopole, then there will be non-zero divergence we can obtain, just like in case of electric field we have obtained that. But in case of magnetic field, the magnetic there is no magnetic monopole, so we can say that that will be magnetic. In case of magnetic field, there will be zero divergence, so that is the zero. These things are discussed in detail in last class. I am just again stating that physical meaning. The third equation, this equation, the Faraday's law means that magnetic field which is oscillating with respect to time, that can generate a electric field. And the fourth law, that means Ampere-Maxwell law, said that if there is a oscillating electric field or flux, that can generate the magnetic field. Okay. So, essentially these two laws, third and fourth law, signify how the electromagnetic waves actually generated, and from that condition we can say that if there is oscillating electric field, if there is oscillating electric field, that means there is a electric field with electric flux or electric field which is changing with respect to time, so it can create a magnetic field. So, oscillating electric field can generate a magnetic field, and that magnetic field, if is also oscillating, that also create a electric field. Okay, and this electric field generates magnetic field generates electric field, this occurs simultaneously, and as a result electromagnetic waves generated which propagates in a perpendicular direction, which the direction is perpendicular to both of electric and magnetic field, which is denoted by the k vector, the wave vector. That k vector is perpendicular both electric field and both magnetic field, as well as that electric field and magnetic field both are perpendicular. So, we have discussed these things in details. Now, in this class, first we will discuss some problem, then we will go to our next topic. Okay, let me find out some problem. So, let us say first problem, some problems. Okay. So, first problem is, let us say I am just writing the problem first. If the velocity of electromagnetic wave in vacuum is 3 into 10 to the power 8 meter per second, and magnetic permeability, that means mu naught. Okay, let me write magnetic permeability of vacuum is 4 pi into 10 to the power 7 Newton Coulomb to the power minus 2 second square. Then it is easy question, find the electrical or electric permittivity of vacuum. Okay. So, what does it mean? It is very easy question, nothing is there. Mu naught is given, mu naught is 4 pi, mu naught is 4 pi into 10 to the power 7 Newton Coulomb to the power minus 2 second square, and they ask to find epsilon naught, provided that C is equal to 3 into 10 to the power 8 meter second inverse. So, now we know that what is the C? C is 1 by epsilon naught and the mu naught. So, from here we can write that C square is equal to mu naught epsilon naught. So, epsilon naught will be 1 by C square mu naught. So, just we have to put the values. Now, what will be the values? 1 by C square is 9 into, if we square the this value, 9 into 10 to the power 16, unit is meter second inverse, and mu naught is 4 pi 10 to the power 7, and what is the unit? Newton Coulomb to the power minus 2 second square. So, it will be essentially 8 point, what is the value, 8.842 10 to the power minus 12. If we do this calculation in calculator, then we obtain that it will be c square Newton inverse meter to the power minus 2. This is the electrical or electric permittivity of the vacuum. From here we can obtain. So, this is just problem 1. So, this was very easy question. Let me discuss some difficult question from NCERT books. In NCERT books there are some problem, right? So, let me discuss that. Okay. The problem 2. Let me first state the problem. A plane electromagnetic wave of frequency is given, frequency 25 megahertz travels in a plane, right? No, travels in free space. Free space along the x direction. Okay. At a particular point, okay, in space and time, that electric field is, that E is 6.3 J volt per meter. Okay. Then what is B at this point? Okay. So, what is given here? E is given, right? E means the electric field. Electric field in the y direction, we can see from this unit vector J. The electromagnetic wave is traveling along the x direction. Let us say this is x. If it is x, okay, let us say this is y, then it will be right. Z direction will be this. So, x, y and z. So, in this way, this is the k vector, the propagation. Okay, let me not write the k signs will. Okay, this is the direction of propagation. Electric field is working along this direction. So, it is known that the magnetic field is perpendicular to both electric field and the direction of propagation. So, you can say that the magnetic field will be present along the z direction. Okay. So, let me first point out that frequency of electromagnetic wave is the 25 megahertz. So, now the frequency is okay, we know that electric field E is, okay, not electric field, the magnetic field is E by C, right. We are just dealing with the magnitude here. Here is the magnitude only. As if there is a vector, then we will denote, we basically denote by the arrow. This is the vector. Now, for the magnitude only we can write like this, or just E means the magnitude. Okay. So, we can write that first we have to find out the magnitude, B equals to E by C, right. So, E is given, what is E? E is 6.3 volt per meter and C is 3 into 10 to the power 8 meter per second. So, if we calculate that, then it will be 2.8 into 10 to the power minus 8 Tesla. So, this is the value of magnetic field, and we have just discussed that magnetic field will work in the z direction. So, we can write that again we can write that because E and B are perpendicular, and also that k and B also perpendicular. K means the wave vector. So, from here we can easily say that B will work along the z direction. Also, we can find out the direction of B from E cross K. k vector, E cross k vector. So from E is plus j along j direction and k is along I along x direction. So essentially it will be plus k. So from here also we can find out, but intuitively also we can say that it will be working on the z direction. So B vector will be 2.1 into 10 to the power minus 8. This k is the unit vector along the z direction, Tesla. So this is the value of magnetic field. Okay. So in this part I stopped here. In next part we will discuss another problem. Thank you.